We're happy today to have a very large-scale structure-oriented Cosmology, and we start with Petter from Technician, from TUM in Munich. He will tell us about the two-loop bispectrum and large-scale structure.
Thank you. Yeah, you can see my screen and you can hear me.
Yes,
right?
yes.
Yeah, perfect.
Yeah, and also we can see the cursor.
Yeah, okay, great. Yeah, first of all, thanks a lot for the invitation to talk today at the Cosmos seminar. I'm very happy to do this, even though not in person, only virtually, but then today I'll talk about a fairly recent work with Tobias Baldauf, Matthias, and Theodore Steele on the two-loop bispectrum of a large-scale structure. And yeah, so as you know, the bispectrum is the leading non-Gaussian statistic of large-scale structure in Fourier space. The shape contains information on, of course, gravitational instability, formation of structure, but it can also be used in testing cosmological initial conditions. So, for example, yeah, inflation and constraining primordial non-Gaussianity, as of course people in the audience did quite recently. And it's also useful in breaking parameter degeneracies because it has information complementary to the power spectrum, so that, for example, it could help breaking degeneracies between bias parameters and cosmological parameters, or, for example, between the mass of neutrinos and the overall amplitude sigma 8, for example. And so, yeah, so in this project, we went ahead and wanted to compute the bispectrum at 2-loop in the EFT of large-scale structure and to see how far we could extend the to n-body simulations. And I think also probably the audience knows quite a bit about the EFT of large-scale structure, but let me also just spend one slide introducing it and also to essentially define the basis in which we write the contributions to the effective stress tensor term and also the notation we use for the EFT parameters, etc. So in the EFT of LSS, you coarse grain your density fluctuations, and then the long wavelength modes solve the same continuity and Euler equation, but with now including also the stress term tau here, which has now been included contrary to SPT, because now in addition to microscopic contributions, you also get contribution from the coarse-graining procedure itself. And in the EFT, this is treated as, or you don't model this from first principle, but you write down operators allowed by symmetry that it can depend on with some coefficients. So in this work, we work at leading order in the gradient expansion, so in the expansion k squared over k, so the non-linear scale squared, and at first and second order in perturbation theory, then we write down these contributions to the effective stress tensor, where at second order there's three additional parameters, E1, 2, E3, and here the S is the tidal tensor, so that we in total have these four EFT parameters. And we also neglect the stochastic part of the effective stress tensor. In principle, though, to compute the two-loop bispectrum in the EFT, we also would have to write down the third and fourth order contributions to the effective stress tensor here. But since we will use a simplistic treatment where you don't need those operators explicitly, we won't write them down. So let me begin by a recap essentially of the one-loop bispectrum, which in the perturbative distribution has these four terms: contributions, corresponding to the 4 diagrams on the upper right here. And yeah, we're with 3 external momentum legs and loops. So for the EFT analysis, you want to look at the UV sensitivity. So yeah, the UV contributions to the one loop. And if we take all external momentum to scale as one overall case, so for example, for an equilateral configuration, then the UV sensitivity comes from the 411 and 321 diagrams, which is this one and this lower or middle right one here, because this has this daisy loops, which give the dominant UV sensitivity, which is proportional to k squared times this displacement dispersion defined here as sigma d squared. And then the other 2 terms would enter as k to the 4th and k to the 6th, with k to the 4th and k to the 6th yeah, overall scale, which would make them next order, etc., in the gradient expansion, so therefore we don't include them in the analysis here. And it was shown in these 2 references some years ago that the dominant UV sensitivities from these 2 diagrams can be absorbed by those EFT operators that I defined on the previous slide with these 4 EFT parameters. And we'll also consider in this work a UV-inspired approach, where we assume essentially that we have that we can write down a linear combination of these 4 EFT parameters, and the linear combination will be inspired by the shape, so by how they enter in the UV in SPT, so that we could write down we could relate all the parameters just to one parameter, which just would be the kind of overall amplitude, and then this one parameter would absorb the hard loops. So in total, 1 4 parameter approach and just one parameter. And before I come to the 2 loop results, I also want to make a detour and discuss this the Einstein-de-Sitter and Exactsteinemann time-dependent dynamics. So in cosmological perturbation theory, it's one typically uses this Einstein-de-Sitter approximation, where you set omega over f squared, where f is the growth rate, to 1 in the equations. And this works very well, both because in lambda CDM this only deviates at very late times because of entering vacuum domination from 1. And in addition, if you take into account the exact time dependence, this does not change the growing mode, so it's only the decaying mode that's changed by taking into account the exact form. And in addition, with this approximation, of course, you get these very nice analytic solutions for the kernels. But we also wanted to check this approximation essentially. So we compute kernels with time-dependent kernels, taking the exact ratio into account. So here I'm writing down the equation of motion for the FNG kernels now with some time dependence, and entering here this x, which would now be time dependent. And while it's I think it's possible to solve this analytically up to quite some, at least, third order, maybe fourth order. I don't remember, but we solve this numerically. So when, for example, computing, say, the B411 diagram that would contribute to the one loop bispectrum, which looks like this, then we have a loop integration here, and we would then integrate this using Monte Carlo integration, and then for each point in the Monte Carlo, we compute this ODE for the kernels numerically, which is also quite complicated because, for example, for F3, of course, this is a hierarchy, so you have to then compute for F4, you have to compute F3, F2, etc. So it's quite complicated and a bit time consuming, but then of course we can also take into account the exact time dependence. So we did this also, I did this some years ago with Matthias, But for the power spectrum, so here on the top, I'm showing exact versus EDS kernels for the 1 loop and 2 loop power spectrum at redshift 0 and at redshift 0.5. But this is just, so this is only the bare correction, so there's no EFT or anything here, just the normalized power spectrum, and therefore the 2 loop very quickly becomes dominant and perturbation theory breaks down. But around 0.1, for example, we have then roughly 0.5% deviation at redshift 0, and at 0.5 the deviation is much smaller, than both because the loop corrections are smaller at earlier times, but also the EDS approximation works better. And for the bispectrum, this is what I'm showing on the bottom here. So we consider 3 shapes: equilateral, squeezed, isosceles. And these plots show the difference between exact kernels and EDS kernels divided by the 3-level EDS bispectrum for 3-level and 1 loop. So this, first of all, the gray line shows that there's a small shift, k independent roughly, between exact and EDS kernels for all shapes. And for 1 loop, we find this few percent, so this is the black line difference between exact and EDS. We find this few percent deviations between the various, for the various shapes. Interestingly, however, we now take the counter terms either for 1 parameter or 4 parameters. Then we can, especially for the 4 parameter case, we can fit this to the difference. So then we see that we can actually very well fit the departure from Einstein-de-Sitter up to maybe 0.15 in all cases, so that the departure can be absorbed into the counter terms. So then let me go on to the 2-loop bispectrum. For the 2-loop, there's 11 diagrams and permutations. I show a couple here on the right with the 3 external legs and now 2 loops. And to analyze the UV of the 2-loop, it's now useful to split or consider the double hard limit and the single hard limit. So you could have 2 cases where one where both momenta become large, and one where only one momenta become large and the other stays at the order of the external momenta. So let me begin by discussing the double hard limit. And again, for the double hard limit, it turns out that this B601 and B521, which are the 2 diagrams I'm showing here, so I'm not showing other diagrams, but these 2 have the dominant k-squared UV sensitivity, and then the other diagrams would then again have k to the 4th, k to the 6th, etc. So we don't take them into account in the considering the double hard limit. And for these 2, we then computed this double hard limit analytically. So also taking into account this F6 operator that would enter in the B601 and obtaining an analytic limit for this kernel. And then we can show that this the shape of the double hard limit then can be absorbed by the same EFT operators that were normalized the 1 loop power spectrum. So the same for EFT coefficients, which is maybe not so surprising if we look at the diagrams here. If we remove the hard loops, then this looks exactly like the counter terms that were there at 1 loop. And we also, we now consider a renormalization scheme where we fit these 4 parameters to the 1 loop, and then we just remove the double hard completely from the 2 loop correction. So we in practice consider this subtracted 2 loop, which is the 2 loop minus the double hard limit, so that there's no additional UV sensitivity at 2 loop that is not already captured and were normalized at 1 loop by fixing these coefficients. And this is also what's shown here on the bottom. So here again for the 3 different shapes, showing I hope this is not too small, but on a log scale here, plotting the first of all the linear bispectrum is this gray line, and then the one loop is the black, and two loop is the blue line, and the double hard two loop is this dashed dotted line, which we can see is the dominant contribution to the two loop if we look at very large scales. And then removing this double hard limit, then you're left with the yellow subtracted two loop contribution for all shapes. Now one can also wonder whether this one parameter ansatz, where you write down, you relate the four parameters in some combination inspired by the UV of SPT to one overall parameter, whether this ansatz can be extended to two loop. But maybe not so surprisingly, how these shapes enter into the linear combination where these shapes enter into the UV of the two loop is not the same linear combination as it was for the one loop, which can be seen here, for example, where this plot shows the ratio of the double hard limit over the hard limit of the one loop for a ratio of two external wave numbers, and then also the angle between those two for different angles here. And the shape is very different, so you couldn't simultaneously, if you pick this linear combination and that can take care of the UV of the one loop in SPT, then you cannot simultaneously use the same linear combination to take care of the two loop. So therefore, this one parameter ansatz cannot just naively be extended. But we include it nevertheless just for completeness in the analysis. Now, so there's still the single hard limit to consider, where either where either one of the loop momenta become hard. And I guess while it's possible to also compute this numerically, it seems quite complex. So we follow we use a prescription that was used for the 2D power spectrum some years ago by Tobias Baldauf, Mercoli, and also Matthias Salariaga. And we essentially go for a numerical evaluation. So if I define this small b here to be the integrand of the 2D bispectrum, where this linear input power spectra evaluated at the loop momenta are factored out. Then if I take, say, Q1 to be take it to infinity, then this integrand would scale as 1 over Q1 squared, which then cancels the Q1 squared in the integrand here, and the integration that is left over Q1 is just over the input power spectrum here. So that essentially I can factor out the Q1 integration, which is what I'm doing in this next line here, where I take I'm taking the hard limit of the single hard limit of the two loop, and this displacement dispersion, the integral over the input power spectrum is factorized out. And then the remaining part is this small b single hard here, which is defined on the next line, where now the remaining part is the integral over the second momentum and the angular integration of the momentum that was sent to infinity. And then the integrand here with the explicit limit. And this whole quantity here we can essentially compute numerically by just setting in the code, setting Q1 to a large value, much larger than the cutoff here. And then this is the quantity that we take as essentially as the counter term. But there's a small caveat, say, in that in this integral, Q2 can also become large, and then we essentially capture the double hard limit again. So this we already captured essentially, so we don't want to have a new double hard contribution here. So we subtract this degenerate part and take the subtracted single hard, which is then this single hard quantity, and subtracting the double hard. So yeah, in total, the counter term we use is then this subtracted single hard times some EFT parameter gamma 2, which then essentially corrects for the mistake in the displacement dispersion. And yeah, so then I'm coming to my results. So we used this realization-based agreed PT method so that we could essentially evaluate the theory on exactly the same modes that were used to seed the n-body simulation that we compared to, so that we can beat cosmic variance and even for like a modest simulation volume. And we have had the one with 4-parameter case, and that 2-loop the same parameters, but now also this gamma 2 that was introduced for the single heart limit. And then I'm also including this UV-inspired approach with just 1-parameter gamma 1 fitting the overall with some taking some linear combinations between the 4-parameter, and this can also be extended taking also the single heart limit into account by just some naive prescription saying gamma 2 is equal to gamma 1. And on the bottom left here, this is the equilateral shape, plotting the difference between the theory and the n-body results, and dividing by the 3-level bispectrum. And here, this red shaded area is the uncertainty from the n-body, and then the various gray shadings are expected uncertainty at theoretical expected uncertainty at the linear 1-loop and 2-loop level. And we can see, so the green and the red lines here are the SVT results, which quite quickly differ a lot from the n-body results, while in the EFT the agreement can be extended quite a bit further, and for the 1-loop it starts to deviate maybe at 0.908, so it's 0.9, sorry. And yeah, so for this is for a pivot scale of 0.115, and the 2-loop can be matches quite well up to the pivot scale here. And on the right, this is taking into account all the triangles in the analysis. So there's roughly, I think, 60 triangles up to 0.1, and then something 300 triangles up to 0.2. So taking into account all shapes in the analysis, and then putting the chi-squared over degrees of freedom. And first of all, this the 1-parameter ansatz cannot really capture the n-body results very well here. So even for both 1 and 2-loop, and there's also these lines which would fix this 1-parameter as the CS squared from a calibration from the power spectrum to the data, but yeah, neither of these perform very well. But the 4 and 5-parameter 1 and 2-loop bispectrum matches much better. So for at 1-loop we have a 1 sigma agreement up to roughly 0.8 h/megaparsec, and then adding also the 2-loop extends this agreement to roughly 1.15 h/megaparsec. And I think I maybe have a few minutes left, so then I thought I would also flash a completely different project just on one slide here, which hopefully is on the archive in a few weeks or something. So we also wanted to take it. So this is a project with Matthias, where we take neutrinos into account beyond linear theory in structure formation. So we consider a 2-component fluid where we have colloid matter and baryons in one component, and then coupled by gravity to degenerate massive neutrinos as the other component. And then we write down the fluid equations at sufficiently late times where neutrinos can be described by a fluid before we use the full Boltzmann hierarchy, just with class essentially at linear, and then at late times we have the fluid for both components, and then we compute loop corrections to the power spectrum at 1-loop and 2-loop in this 2-fluid setup essentially. And what we do then is a similar, we compute this in a similar way as what I mentioned previously with exact kernels versus Einstein-de-Sitter kernels, that we when we compute the loop integrals, we for each Monte Carlo point then solve the equation of motion with, numerically for the kernels. And now these kernels are more complicated because it's a kernel for the two component fluid, and then do the integration. So it's very much slower than the EDS, but then we can also capture the effect of neutrinos beyond linear theory. So we do this at one loop and two loop, and then we compare to just taking neutrinos into account at the linear level. And this plot on the bottom left here, or both these two plots, is taking the linear treatment of neutrinos and dividing it by the full two-fluid solution. At dashed lines would be at one loop, and then the solid lines are two loop. This is now, and for different neutrino masses, and this is the power spectrum for the density contrast of the cold dark matter baryon component, and this is the velocity velocity power spectrum. But this is still now, so this is just the bare and normalized quantities. So again, going to large scales here, the perturbation theory breaks down and the two loop difference becomes very large. But on smaller scales, we have less than a percent deviation here. While for the velocity spectrum, the difference is quite a bit larger, at least for taking the largest neutrino mass of 0.4 eV here. And we suspect this is because now in the massive neutrino case, then the growing node, the propagator, is not there's an additional suppression in the velocity component in the propagator due to the reduced growth in the massive neutrino cosmology than in just the massless case, which then gives an additional suppression to the velocity component. But here again, the perturbation theory also breaks down there for the bare quantities. And then finally, we compute this also in the EFT and compare to Kirchhoff data for just the power spectrum, the density power spectrum, which is shown here. So dividing by the Kirchhoff results with the gray areas, just some simple variance from realizations. And now this one fluid will be the linear treatment of neutrinos, and the two fluid the full nonlinear treatment of neutrinos. But since now we have the freedom of the EFT counterterms, this difference can really very well be fitted so that both models seem to match the data essentially equally well in this case. So so with that, I come to my summary. We computed the two-loop spectrum in the EFTofLSS, and we also discussed the departure from EDS and to what extent it can be absorbed by counterterms. And for the two-loop, the double hub regions can be captured by the same EFT operators that were normalized in one loop. But for the single hub region, we use this simplified treatment where you only need one additional parameter. And then fit into an poly, we find that at one loop we can have a good match at up to roughly 0.07, 0.08 H megaparsec. So this is a redshift 0. And adding also the two loop, then we extend this wave numbers with agreement of 1 sigma up to 0.15 H megaparsec. Okay, so thank you very much.
Thank you, Peter, for the very nice talk. Are there questions? Oh, yes, Misha, please.
Yeah, thank you, Peter. Great talk. So I had a question about this simplified treatment. So in principle, you said that like for the n-body simulations that you're using, like if your data set is only the bispectrum, then it's enough to have only one additional counter term to fit the data. But in principle, if you were to, go in full generality and like write down all possible operators that can appear in the stress energy tensor at the
Right.
two, like how many counter terms would you find?
Yes, I wanted to say this was also my question essentially. So thanks.
Yeah, that's a good question. I don't have an answer, I think, because I haven't. We didn't write down all the terms at third order and fourth order, etc. So I wouldn't know, unfortunately. But it would be interesting. I'm not sure if I have any intuition in how many necessarily would be like, but yeah.
Yeah, because my worry was that for the two-loop power spectrum, I think that the statement was that the number of counterterms grows factorially. So like really, you have many. I don't know. Maybe you can have already like 20 or something. That might be. I mean, on the one hand, if you only use the bispectrum data, you might not have enough data to constrain all these counterterms. But if you have, the whole array of observables, like the two-loop power spectrum, like the two-loop bispectrum, let's say one-loop trispectrum, like with all these different data sets, I think you should be able to like really constrain all these counterterms that appear there. And like if you go for these general data sets, I think that you have to go fully generically and like really to write down all the operators.
Yeah, sure. Yeah. But I guess, so at the moment, I guess this is, with the current simulations and better than me with the data analysis, but this seems to be at least, I guess the best one maybe can do at the moment, or at least one method of for normalizing the two group that seems to work well, at least in this case.
There is a question by Anton.
Yes, Peter, I would, regarding the last part of your talk about the neutrino, I want to ask about what kernel do you use? It's EDS kernel, or you include the scale dependence as this kernel?
No, I'm tempted to. Okay, I don't have this in an extra like backup slide or something. No, so it's not EDS kernels. So if I essentially
lambda CDM. You called this lambda CDM kernel, am I right?
So it's I would now okay. So with the two-component fluid, then I essentially say that I have, instead of just two kernels, I have four kernels. So I have a kernel FMG for the CDM component, and then kernels for the neutrino component that would take into account nonlinear corrections to the neutrino distribution function, so that I would write down essentially 4x4 system where I have four kernels, and then this would be four equations with taking the same, or taking the nonlinear vertices are the same for the neutrinos. I mean, those are equivalent as for the CDM component, but then we take into account a sound speed for the neutrinos, so that we capture the free streaming of the neutrinos, and then also this the gravitational coupling between the complementary component and the neutrinos. And then this is both scale and time dependent. So here it's just time dependent, but then we do also have a scale dependence, so that it's even more complicated. Yeah, sorry.
Yes, but how is actually important? I mean, if you reject this, I mean, if you just use the EDS kernel, did you get the right result or not?
So, the results so far seem that because of the freedom in the counterterms, at least for the power spectrum, then these differences can be absorbed into just into the counterterms. At least at the level where the certainty we fit to the Kirchhoff data at the moment. I'm wondering, however, what would happen in redshift space because of this difference that we find for the velocity spectra, but this we didn't check. And I guess also the lowest neutrino mass is probably the most realistic, and then the difference is also quite less than 1%.
Okay, up to suborder level of accuracy, it can be absorbed by counterterm, you say. Okay.
Yeah.
Sounds nice. Yeah. Thank you.
Yeah, I guess the point is maybe to try to also to just scrutinize all the approximation and check that it's.
Yes. But actually, to what percent can be absorbed? To sub percent? How precise? I mean, it can absorb. The counterterm can absorb the scale dependence of the kernel. Because on this plot you show the green and blue lines. That's what I asking for or not?
Yeah, so I mean here the difference would be very small compared to the uncertainty of the embodied, so then I don't think it makes Yeah, then
I see,
it becomes a bit of a question of the fitting here. What we could do, of course, which we didn't get, is to compute, which it's just to, I mean, fit this difference that we get here for the Bayer quantities to the counter terms in a similar way.
Peter, but I mean that your plots, blue and green line, actually includes the accurate.
Maybe Anton, if it's okay for you, maybe we can just we can say later and actually, yeah, I'm happy to. We can say later and continue discussing. So if it's okay for you, thanks Peter again for the very nice talk, and we can go to Anton indeed, and then anybody who wants to stay and after the talk we can discuss more.
Sure. Okay, do you see my screen?
Yep, perfect.
Great.
So perfect. We're happy to have Anton Chudaikin from McMaster University, and who's going to tell us about theoretical modeling of PDF of cosmological counts in cell. So please, Anton.
Yes, thank you very much for having me. I would like to tell about something complementary to what Peter told, actually about the theoretical modeling of non-perturbative statistics. The main object which I will be talking about is a probability distribution function, which represents the probability that a cell of a given radii has the average density contrast delta star. Actually, one can use the saddle point approximation to predict this observable, and the leading part will be described by saddle point solution. In our case, it will correspond to the spherical collapse. And the next to leading order correction to the solution is will induced by the perturbation on top of the saddle point solution. And it boils down to the determinant or prefactor in front of the spherical part. And the relevant parameter here in this expansion is actually the smooth variance of the density field. And as long as this parameter is small, the saddle point approximation can be safely used to predict the PDF. And I will verify this condition on the example of the n-body data as follows. Okay. Let's start from the theoretical point of view. The PDF can be modeled in the path integral formalism. One just need to average all initial conditions delta linear and weighted with the Gaussian distribution of this field and multiplied by the delta function, which selects only those delta linear which reproduce the delta star, target delta star in a cell of the time of interest. And actually, the spherical configuration passes through spherical collapse solution, and the solution can be easily found. It's called the exponential form. And of course, one also has the perturbation on top of the solution, which modifies this scenario a bit, and it boils down to the following prefactor in front of the exponent part. The monopole part can be calculated precisely. Because we know the model for the spherical collapse, and but a spherical prefactor can be calculated numerically, and it was done rigorously only recently in 2019 by Misha, Sergei Sibirikov, and Sasha Kaurov. Okay, but before moving further, let me verify that the saddle point approximation really works. For this, I just extract the spherical prefactor from the data. And just divide the data point by the spherical part calculated theoretically, and present the result for the different cell radii. And we found that semi-classical is there for even down to very small cell radii. For example, for 600 kiloparsec, its semi-classical scaling is valid, and it's very impressive because the cosmological perturbation theory is valid only until 10 megaparsec or so, and it cannot be pushed forward. And it's proves that the PDF can bring complementary information from nonlinear scales. Let me just present the results for calculation, numerical calculation of fluctuation determinant for different cell radii. On the left-hand side, you can see these plots for 3 different cell radii. And it's worth to mention that the amplitude of the aspherical prefactor and the tilt in the origin is controlled by symmetries, specifically by the conservation of probability and translation invariance. It also weakly depends on cosmology, and it's very practical because you can calculate it only once, and there's no need to calculate it, for example, in each step of the MCMC approach in real data analysis. Okay, our next step will be just confronting the theory to the data itself. Here you see such a comparison, and in the origin of the prefactor, you see that the theory prediction matches the data very well. But on the tails, you see the discrepancy. You see that the data, we see that the theory over predicts the data, and we attribute this effect to the short wavelength modes because we don't have the reliable theory for them, and it just means that their contribution must be renormalized. Just one loop correction to the power spectrum is renormalized by contagion. And the renormalization of the spherical prefactor is the main result of our work. Okay, but to renormalize the prefactor, we need to shell crossing scale at which two flows in the hydrodynamic approach cross each other for the first time, and when the perfect fluid approximation completely breaks down. To do this, we just follow one particle with respect to the conformal time and found the divergence and found the total displacement of the trajectory inspired by the spherical fluctuation, and use a very simple model for the shell crossing scale. We assume the shell crossing scale happens when the divergence of the total displacement squared equals to 1. And then one just need to summarize overall multiples and integrate overall initial conditions, which boils down to integration of momentum. And under assumption of the power law of the power spectrum, one can obtain very simple expression for the shell crossing scale. I emphasize that this shell crossing depends explicitly on the background configuration of saddle point solution. This is the main point because it's correctly captures the physical properties of the system. For example, on the left side, you see the plots of the such a called contact term in the curved background, and it's higher in overdense region than, but at the other dense region it's less than that in the flat space. It is much our naive expectation what would expect from EFT on the curved background. Also, the linear growth factor can be obtained in a similar way. It also depends on the saddle point solution explicitly, and we fixed in our consideration everywhere power law index equals to -1.5. It's the conventionally reduced value in Felice region. Okay, say several words about the effective stress energy tensor. We just split all quantities into long wavelengths and the short wavelengths quantities, and integrate out over short wavelengths contributions by simple prescription, just by integrating with some kernel, which equals to 0 in long wavelength limit, and obtain the following correction to Euler equation, which you see on the right-hand side of it. Each described by the stress energy tensor of a spherical fluctuation, and it consists mainly of two parts. First one called the kinetic induced part. Each part is responsible for the formation of the shell crossing, and the second part is called the gravitationally induced. It's crucial for decoupling of the virial scales from long wavelength dynamic, and also should be taken into account as there is no physical reason or theoretical from the theoretical perspective that this contribution should be 0. When we make very important assumption about the dispersion of the velocity field in the first part, in the kinetic induced part, we assume that the velocities of the flows doesn't change significantly in the shell crossing. And it allows us to express the dispersion velocities in terms of the quantities in perfect fluid approximation. Finally, we move to the contact model itself. We just translate, modify the rewrite conservation equation and Euler equation in terms of mass and radius of the shell, and found the following equations. And on the right-hand side of the modified Euler equation, you see the sources. The sources actually comes from the stress and energy tensor, and they explicitly can be found. You can see below the explicit views. And since this term comes from the different parts of the stress energy tensor, which describes the different physical processes, we treat them separately and solve this system for each of them.
Sorry, Anto,
yes.
may I ask a question? Like,
yeah, sure, you can ask.
These equations are then on a curved background. I'm missing a bit. Like, are these equations on a curved background or not?
Yes, this equation on the curve, it's like the conservation equation and the other equation on the curved background.
Okay,
yes.
okay.
On the curved saddle point solution. First, we find the saddle point solution, and then we perturb it and find the evolution of the perturbation. But then we rewrite it, of course, in terms of these quantities.
Okay.
It's very easy to find in these terms.
Thank you. Yeah.
Okay. And we treat this, as I mentioned, we treat these two terms separately, and we solve the system twice for each of them and find two different quantity terms. And of course, because we don't know the precise amplitude of these two contributions, the stress and energy tensor, we following the EFT approach, we introduce the free parameter alpha and beta in front of each source and multiplied it by the contact term in curved background. Okay, on this slide you see our final solution for two shapes of two quantity terms. Comes from the different part of the stress energy tensor. Here you see that both of them always less than 1. The derivative at the origin equals 0, and they suppress the probability more strongly at overdense regions than at the underdense region. It's also meaningful because in an overdense region you have highly nonlinearities, which requires more stronger renormalization. As a result of that, the quantity term is bigger. On the, is smaller, but the effect is bigger. And also for the small radii, you have more enhanced suppression because it also makes sense because for smaller radii you have more stronger non-linearities, which also require more stronger renormalization. Okay, let's just summarize our theoretical model, which consists of the three main parts. But actually, we will work with the spherical prefactor. We will confront it from we will confront it to the data, extracted from the data, and that's why we reformulate our model in the following way. Here you see contact term comes from our two-parametric model, which I presented on previous slide, and actually the freedom of this model can be restricted to one parametric family because the second derivative of the contact term is fixed by sound speed measurements as a common EFT parameter to power spectrum, to one power spectrum. And if one knows this parameter, one can fix the second derivative of the contact term itself. And that's how we exactly proceed. We extract the sound speed from the power spectrum of n-body simulation and found the relation between alpha and beta. It means that our quantum model effectively has only one free parameter. And it's very practical. It allows you, it significantly simplifies the model and actually help to avoid the overfitting in the real data analysis. And several words about time dependence of our contact term. We found the following, that the contact term can be rescaled from the present time to any redshift under consideration according to this simple formula. It's very practical to use it because we need to calculate the contact term only at one redshift and then translate it to anyone you want. And of course, we will validate this prediction with the n-body simulation later on. Okay, several words about the fitting procedure. We fit the spherical prefactor extracted from the data using our theoretical template for fluctuation determinant at contact term model. And we assign to the data the following Poissonian covariance. And we've also theoretically marginalized over the model parameters, in particular the index n and the sound speed. We assume the Gaussian distribution for them, and their variance and cross correlation are extracted from the data. Okay, let's finally move on to our final result. Here you see the results for the cell radii 15 megaparsec over H. Blue line represents the theoretical modeling without contour term. Within dashed red line represents the full renormalized theory. And you see that the full renormalized theory matches the data very well on the whole range of the density contours, which we consider. It proves our idea that the aspherical prefactor must be renormalized, and without it, it will be biased. It will give you biased result. Then we move on to the smaller cell radii, 10 megaparsec over H, and found the perfect agreement between the data and the theory. And it's actually our best case scenario because the statistics of this cell of such a radii are significantly better, and at the same time, the higher order loop correction remains small. Okay, we move even further. We apply our theory for the cell radii 7.5 megaparsec over H and found the mild discrepancy between data and the theory. It can be more evident if one looks at the origin of the prefactor. And we see that this difference becomes larger for smaller redshifts. And it actually resembles, and we attribute this effect to higher order effects, which missed in our model, because they also become important gradually as the redshift decreases. To validate this conjecture, we consider even extreme scenario of cell radii equals 5 megaparsec over H, and found that our theory cannot explain the data, cannot fit the data. At the origin, we found the strong evidence for the higher order loop correction, and the effect becomes stronger as the redshift decreases. And I would like to emphasize that this correction cannot be explained by improper modeling of our contour term model, because the contribution of the contour term at the origin should be 0. And it's exactly come from the higher order correction. And I just to emphasize once again that to obtain the reliable results, one need to include the theoretical error of PDF, but for this one need to calculate 2 loop correction to the probability distribution function, and we leave this task for the future work. But anyway, even in this worst case scenario, our model reproduces the data within 15% accuracy. I think it's quite impressive because the previous model describes the data only at 30% accuracy, and it was at much larger radii. Our model works in 15% accuracy at 5 megaparsec over H. It's extreme like case scenario. Okay, and let me summarize. I just try to convince you that next really node correction can be straightforwardly calculated. And the aspherical prefactor, which calculated from, determinant of the response matrix must be renormalized, and we suggest 2 model parameters for this. And we reveal that these 2 model parameters describe the data perfectly for large cell radii, but for small cell radii, we found evidence for nonlinear correction, higher order loop correction, 2 loop, or even higher, which missed in our model. And to find the reliable result, we need to include the theoretical error covariance to our model. And anyway, is for 5 megaparsec, our model presents the worst case scenario 15% accuracy. It's for PD for 5 megaparsec. Yes. That's all. Thank you.
Thank you, Anton, very much for the very nice talk. And also, thank you for staying very much on time, I see. So are there questions for Anton?
Everybody is very clear.
No, I had like a generic. Can you maybe we go to the second slide, or
yes, wait me a second. I just turn my system. Yes, second slide.
Yep. Oh yeah. Oh, no, then it was yeah that one after. This,
okay.
I think.
After this one.
I think this one. So,
okay.
so here So this delta L, I'm a bit.
Delta L is yes, is the initial linear.
Is initial linear, the full linear field. So this is a full function, but this delta 1.
Delta 1 where?
This Dirac delta is a Dirac delta of in one dimension because delta star is just a number, right? Or this is so it's a very complicated.
Actually, we measure delta star as we measure on the experiment delta star. Do you hear me? It's not my problem. I thought it's my problem. It's okay? Giovanni, do you hear us?
Yes.
Now, yes. I just wanted to mention, I wanted to emphasize that delta star, yes, it's real nonlinear density contrast, which we measure at the time of interest. But delta linear is the initial field from which you convolved, I mean, from which you obtain the delta star at the final time. But delta linear is the initial state.
Yes. So I don't know if you heard me. Then I don't understand if I jumped. Most likely, sorry for that. But yeah, I see. I see that this delta V, this delta W is like this filtered.
Delta W is actually also fine because you should convolve from the initial time to the present time. Yes. First you convolve from the initial time to the present, and then you integrate it over the some kernel.
It's a function of okay.
Yes, which represent our sphere. It's actually heavy side function in configuration space.
Okay. Yes, and then essentially what you do is you compute this path integral in the point approximation.
Actually, what we do, we compute the next leading autocorrection. The spherical path, yes. But it's well known, yes. We compute the determinant of the response matrix specifically. But actually, our main result is renormalization of this calculation.
No,
because it also has been done by Misha, 3 years ago.
There was just, I understand that, but I wanted to understand the full setup, the general setup, if you will.
Okay. Nice.
Okay. Thank you. Are there other questions for Anton? If not, then thank you everybody. And we can thank our speakers again for the very nice talks, and see you then next week. And I also invite everyone that wants to, since there seem to be interesting questions also between the speakers, if they want to stay online for a while and chat, everybody that wants also to stay is free to do so. I will stop recording now, and then